Welcome to Quantum Photonics. Welcome to our forum on solar activity, a fascinating and dynamic subject that lies at the heart of space weather and has profound implications for life on Earth and our technological infrastructure. As we delved into the intricacies of the Sun, our nearest star, we uncover a world of immense energy and complex processes that drive everything from beautiful auroras to potential disruptions in satellite communications. Solar activity encompasses a range of phenomena, including sunspots, solar flares, and coronal mass ejections. These events are manifestations of the sun's magnetic field interacting with its plasma, resulting in spectacular and sometimes unpredictable displays of power. The sun operates on an approximately 11-year solar cycle characterized by varying levels of activity, which scientists closely monitor to understand their effects on Earth. The study of solar activity is not just about appreciating the sun's natural beauty. It is crucial for predicting and mitigating space weather impacts. Solar storms, for instance, can interfere with GPS signals, affect power grids, and pose risks to astronauts. By exploring this topic, we gain insights into the mechanisms driving these events and develop strategies to safeguard our technology dependent world. And what more, proper and fitting to have a master of this topic be here as our guest speaker in quantum photonics, Professor Alexander Lazarian. So he is a professor of astronomy at the University of Wisconsin-Madison with a joint appointment at the Department of Physics. Dr. Lazarian started his research in theoretical physics in this group led by Professor Vitaly Ginsburg. And soon after his diploma work, he got a Soros Fellowship to spend 1 year at Oxford University. He later got his Isaac Newton studentship to do his PhD at the Department of Applied Mathematics at the University of Cambridge. And upon getting his PhD from Cambridge, he stayed for a short period in Austin and Harvard, and later he had his 3 year postdoc in Princeton. So after Princeton, he got a 5 year fellowship at the Canadian Institute for Theoretical Astrophysics, or CITA, but spent only 1 year there as he got a job offer for being a faculty at University of Wisconsin in Madison. And he lives and works in Madison since 1999. And he's very, very passionate about his work. So his research interests are in MHD theory, reconnection, dynamo theory, interstellar dust alignment, microwave emission, interstellar turbulence, on statistical studies of it, circumstellar regions and comets on polarization, molecular clouds on the dynamics. So he is a Google Scholar with so much citation index, and his publications are, of course, here in NASA Astrophysics Data System, PH, and in ResearchGate. So without further ado, I bring back to you a very great speaker, a great scholar, Dr. Alex Lisarian. Alex, welcome to Quantum Photonics. Alex, you can speak
Oh,
now.
hello?
Yes, we can hear you well.
Okay, fine. I'm pleased to give my second talk on at this platform. And today I'm going to talk about solar activity and its influence on our civilization. If you look at the second slide, you can see the sun god in Egypt. On the third transparency, you can see the sun god in Greece. On the fourth transparency, you can see sun goddess in India. On the fourth transparency, or probably it's already fifth, you can see the Mayan sun god. What does it mean? It means that sun played a very important role in the development of the human civilization. And therefore, humans understood that sun is giving life to them and associated the sun with something essential, with the god. Well, our sun was formed by gravity, magnetic fields, and interplay of these forces. So it has planets and the sun. Sun is the center of the solar system, and it contains essentially all the mass of the solar system. Sun mass is more than 300,000 times mass of the Earth. So you can understand that the Earth is a small dust particle compared to the Sun. At its early evolution, Sun was a T-Tauri star. T-Tauri stars are special stars which, at the beginning of their evolution, have accretion and jets. But all of this material ejection is happening due to magnetic forces. The sun, solar system initially was a dusty disk, and it had the sun in its center. So, if we go to the slide number 10, you will have an illustration of how sun is getting its energy. It consumes in the process four hydrogen nucleus, protons, and then this four hydrogen nucleus eventually get into the helium 4. The energy which is coming from this reaction is the energy which comes from the defect of mass. Mass and energy are related to by a famous relation E equals mc squared. And the mass of helium is less than the mass of the four protons. As a result, we have a lot of energy being released. Humans only can use this reaction to kill. This is they can use it for thermonuclear explosions, and now with a very dangerous world, we are now standing very close to a nuclear catastrophe. We do not understand this, but we are closer nowadays that the world was to the nuclear catastrophe during Caribbean crisis. It's I like to compare this with the analogy of a frog. You know, if you throw a frog in a boiling water, it will jump out. But if you increase gradually temperature, it will be cooked. What I think is happening now with the war in Ukraine, we are being slowly cooked. We are slowly approaching the nuclear catastrophe. Okay, but we should do what we can. And in this lecture, I'm going to talk still about science rather than this reality that surrounds us. We are not politicians, for better or worse. Well, Sun has another 5 billion years to be as it is, mostly as it is at the main sequence. And then it will become, in 5 billion years, a red giant. A red giant will have its radius probably of the order of 1 astronomical unit. So it's more likely that the Earth will be engulfed in the red giant star stage of the Sun. If there is any life on the Earth by that time, the this life, human life, hopefully can move to more distant planets or leave the solar system altogether. After 7.6 billion years, our sun will become a white dwarf, just cooling a small object which is cooling slowly and emitting its radiation, and its energy will be just internal heat. Okay, if we go to slide 12, it's an explanation that all Earth's biosphere depends on sun's energy. Sun energy is coming, it's absorbed by the atmosphere, but mostly by the planet's surface. It's reflected, it's also emitted at a longer wavelength in the infrared, and this makes this planet habitable. If the Earth is pretty comfortable for humans, its mean temperature is 14 Celsius, which is 57 Fahrenheit. But if you take the atmosphere, it will be much colder. It will be minus 18 Fahrenheit or 0 Celsius. And why is that? It's because of the greenhouse effect. There is a lot of talking now about this pernicious effects of the greenhouse effect. But if we did not have greenhouse, we would not have our oceans. We would have just a snowball instead of our Earth. So it's all good, but it should not be too much. That's the idea. So what's happening with the sunlight in the atmosphere? There are different processes. There is a reflection from clouds, important. It's also reflection from the surface of the planet, and also absorption of radiation and radiation at infrared. If we go to slide 15, we'll see that different planets are subject to different effect of greenhouse. Our planet has the increase of its temperature by about 15 degrees of Celsius. But Mars, it's a bit further from the sun, it's true. But the most important that it does not have atmosphere, and therefore its temperature is minus 50 centigrade. At the same time, Venus had too much of greenhouse effect, and it was an avalanche of greenhouse. As a result, its temperature is 420 degrees Celsius of the planet. It's pretty high temperature. Venus contains atmosphere 96% of carbon dioxide. You can ask, how could it be? Why is that? Why we have a very different content of carbon dioxide in our atmosphere? Usually people say, oh, we have plants. Well, plants are not the most important ingredient here, and we should keep this in mind. Most of carbon dioxide is absorbed by limestone and other reactions with the Earth's crust. So there are different projects around the world. Let's take this carbon dioxide and pump it in some cavities and store it. It's much better idea if we want to get rid of carbon dioxide is to think about natural chemistry, which been which been happening in the Earth history. So many stones can absorb carbon dioxide. For example, as I said, limestone. So let's go to the slide 16, and I will describe you this catastrophic greenhouse effect which happened in Venus. It has 97% of atmosphere in carbon dioxide. But this atmosphere is much denser than the Earth's atmosphere. It 100 times more gas. By the way, in Earth, in the Venus atmosphere, it's only 3% of nitrogen, but it's more atoms of nitrogen there than in the Earth's atmosphere. It's just because there was no this water cycle which absorbs carbon dioxide that nitrogen has only 3%. There is very little water in the Venus atmosphere, and the reason for that everything is very hot, and there are some chemical reactions which make hydrogen leave the Venus atmosphere. The question that definitely is worrisome: could we make this with our planet? Could we have a runaway greenhouse effect with our planet? The answer to this question is given to you at the slide 17. No, we don't have such risk. There were periods where the atmosphere had significantly large greenhouse effect, but this did not result in the evaporation of the oceans and all other effects which could result in the greenhouse effect. Nevertheless, we should be careful not to overheat our planet. And I will discuss why it is important later. But on the slide 18, I'm telling you that apart from other reasons, for example, lower gravity, Mars lost its atmosphere because of the interaction with the solar wind. And this interaction, in our case, in the case of our planet, is mitigated by the existence of magnetic field. Earlier, Mars also had magnetic field, but now when it lost its magnetic field due to some processes inside its core, it started losing its atmosphere faster, which resulted in Mars being not inhabitable, at least for us at the moment. And this, by the way, brings us to another important subject. This is the main subject of my talk. This is related to magnetic field. On the slide 19, I am explaining that magnetism of the planets and the sun is different from the magnetism that we are accustomed to deal with, for example, in our daily life. It's not related to some iron, but it's related to motions of conducting fluids. I don't have time now to discuss how this dynamo works, and there are a lot of controversy how real dynamo works. But for the purpose of my talk, it's important that the sun produces its magnetic field through this dynamo process, similar to the Earth. At the slide 20, I'm showing you magnetic loops created by magnetic fields of the sun. And on slide 21, you can see prominences which are seen in this magnetic structure. At the lower part of the slide, you can see this white dot. It's Earth, and Earth is tiny compared to these prominences. So, these magnetic fields are turbulent, and they are at the core of the solar activity. Sunspots are caused by flux tubes of concentrated magnetic field. And this sunspots are seen darker on the surface of the sun, not because they are not hot, but they are cooler compared to the surface of the sun around it. So if you take material of the sunspot and bring it to the Earth, it will be shining like crazy. But in comparison with a high shining sun, other parts of the surface, it looks dark. The sunspot spots were observed by scientists all over the planet, Chinese scientists in particular. But during medieval time, sun was considered an ideal sphere. And it was Galileo who rediscovered sunspots. The number of sunspots is changing. It's not, predetermined law, but in general, an 11-year solar cycle is observed. And the solar cycle is related to the number of solar spots, sunspots. And these numbers first increase and then decrease through the cycle. The cycle is different from the, for example, cycle of rotation of the Earth. It's not so stable. Sometimes, and I will discuss this later, the sunspots can disappear from the sun surface, and this can have significant effects on the Earth. Well, the change of the sun luminosity due to the sunspots is minimal, and therefore we should not worry about that. But at the same time, there's arches of magnetic fields between sunspots really somehow subject to reconnection, annihilation of magnetic field. As a result of reconnection, magnetic energy is being transferred to other forms of energy, in particular uh, to kinetic energy and of plasma, ionized gas, and to uh, uh, population of highly energetic particles. And this is events related to coronal mass ejection. And this is illustrated at slide 24. Many years ago, with my colleague Ethan Vishniak, we suggested a model of turbulent reconnection, which explains how this release of magnetic energy can happen fast. My former postdoc, Gregor Koval, now a faculty in São Paulo University in Brazil, um, uh, confirmed this prediction through magnetic MHD simulations. If we go to the slide 26, we'll see what's happening when these energetic particles come to the Earth. They create the phenomenon which is aurora. Uh, these phenomena are concentrated at the North Poles. Why? Because the particles ejected, high energy particles, are moving towards the Earth. They interact with the Earth magnetosphere, and some of them are getting trapped by the magnetic field lines, and they are focused at the poles of the planet. So this events are called aurora borealis if it's northern lights, and aurora australis if it's happening in the southern hemisphere. The corresponding pictures are shown on slide 28. This aurora can be seen from the space, from the satellites. It's also present in other planets that have magnetic fields. For example, there is there are these auroras on Saturn, and this is illustrated on slide 30. On slide 31, we see auroras at Jupiter. Well, this is all very nice. People sometimes travel to the north to observe this great events of aurora. This is wonderful, but is it so benign? Not really, because we live in the world of technology. And when we have these particles coming, they disturb magnetic field, induce different effects, and this is pernicious for our technology. It can damage spacecraft's electronic, can affect communications with planes. Sometimes it can result in even short circuiting. So it's not so good. And this is illustrated at the slide 32. Well, you can understand that the solar flares carry a lot of energy. A typical solar flare releases maybe several million times the world's annual energy consumption. And this release is happening in a few hours. The most powerful recorded solar flare is Carrington event. It happened in 1859. During that event, this aurora was seen at the equatorial regions. So all the Earth was shining with aurora light. There were also short circuiting and sparkling from the telegraph. It was amazing for me that to know that at that time there was this cable from Britain to Australia. Can you imagine? You cannot send this signal from over a wire of such length because it will be damped by resistivity. So you can. It's still difficult for me to imagine that at that time in 1859 there was a cable across the whole planet, and every several miles there were so-called relay station amplifiers. These amplifiers had batteries which you need to change. You should get them back by a ship and put new batteries because you need to replace them. So it was a really amazing thing, marvel of the world, I would say. Well, you can ask, Carrington event, was it the largest event in the history of our planet? Surely not. There was at least one much stronger Carrington event, stronger by 1,000 times than the Carrington event. And it was discovered to happen between 774 and 775 year of AD. So it was found through studies of the isotopes of Japanese cedar tree, because this bombardment of by this energetic particles can produce this isotope. This and larger superflares, and there's a slide 34, can be dangerous for biosphere. Well, it means that we need to have a way to predict when these particles reach the Earth. And it's also necessary not to overdo it. The sun is always active, but sometimes these particles coming to the Earth are bad, they're pernicious. Sometimes they're benign. There's not many particles coming. What could determine how many particles come to the Earth's surface? First of all, it depends how many particles are being released, and then how they propagate. And it means that we need to know well the propagation of particles and also acceleration of particles during the reconnection events. A lot of my studies are exactly about these two processes. And hopefully, eventually, by observing this activity of the sun, we can predict, oh, in a couple of hours there will be these particles coming, and we should be better prepared for that. We switch off sensitive equipment on satellites, and in the case of very dangerous event, we also may have take some precautions in terms of plane communication. Okay, well, this is technology, but what about the life itself? Life itself is on our planet is affected by climate, and climate is also being affected by the magnetic activity on the sun. And this is illustrated by the slide 36. First of all, these accelerated particles can affect the ozone layer. So we can, if there are more particles, then there will be a change in the ozone layer, less ozone, then more ultraviolet particles can come to the Earth's surface. Then, during the solar activity period, the change of the total solar luminosity is negligible. But this uh, regions of reconnection accelerate particles, induce emission in far ultraviolet radiation, and this emission can increase 10 times, which also can have a biological effect. This was slide 38. 39 slide illustrates that solar cycles can influence La Nina effects in the Pacific Ocean, and this can change precipitation and winds in the area. We do not fully understand all the effects of sun magnetic activity on Earth's climate, but we know a couple of facts. And this is my slide 40. There was a period registered in the history that there were very few sunspots, and it was from 1645 to 1725. It's this period is called Mount the Minimum, and guess what? This period exactly corresponds to a period of very cold climate. It's called Little Ice Age. And this was my slide 40. On slide 41, you can see Thames River. You see this ice, people jumping on this icebergs essentially on the Thames River. And this was freezing happening during the low sun activity. I just stress again, this is low sun magnetic activity. Sun was shining still as it is, not changing its total intensity much. Interestingly enough, and this is my slide 42, the Napoleon's invasion of Russia coincided with also a colder period, which is related to the Dalton minimum of solar activity. Napoleon was a great leader, a scientist, but he was not aware of this solar cycle activity. Otherwise, he would not invade Russia when he invaded. This was not an ordinary winter. 1812 in Russia, it was very, very cold, even in Russian standards. Okay, but this more shorter time period of climate variations. Let's go to slide 43 and see a longer, larger time scale variations. And we can see that there was little ice age, but there were also periods of much significantly larger temperatures. The temperatures were 2 degrees, 3 degrees larger. And it was happening in this last several thousand years. And if we go to the past 12,000 years, we can see even more significant changes of climate. It's also should be recognized that when we are talking about the variations of climates, and this is my slide 44, this variations of climate can happen sometimes in a few decades. Just several decades, you can have a dramatic change of temperature. We do not know why it is happening, but this was happening without any human interference. This is just part of the Earth's natural history. Well, if you go to slide 45, you can see photos of two gentlemen who try to explain these variations of climate by the interaction of our atmosphere and high energy particles, cosmic rays, which are coming from the galaxy. They analyze the times of different periods on the Earth, and this is my slide 46. And they found that there are ice ages when the Earth was covered by ice, and there are warmer periods where there was no ice. And they correlated it with the solar system going through spiral arms. So when the solar system goes through the spiral arms, the flux of the cosmic rays in spiral arms and between spiral arms is different, and therefore it can modulate the flux of the cosmic rays bombarding atmosphere, and this can change the climate, because there is a very good correlation, as is shown in this scientific paper by Shaviv et al. This is slide 46, an important slide. Well, now let's consider how can cosmic rays change the climate. There is some particular effect. When a cosmic ray passes through the gas, it ionizes the gas. These ions can act as seeds for condensation of water vapor. If this water vapor, as it happens in higher parts of the atmosphere, is overcooled, there is a condensation on this tracks of cosmic rays. What does it mean? Imagine you have the water drops in the high atmosphere. These water drops start reflecting sunlight. And as a result, less sunlight comes to the surface of the planet. What does it mean? It means that it's getting colder. Okay, so in this case, it explains how can we have this ice ages or warmer ages between in the periods when the solar system passes through the spiral arms and inter-arm region. So this is explainable, but is it possible to explain this way the changes at a smaller time scale? On slide 48, I show again this scientific paper result, which shows the flux of cosmic rays correlate with the observed cloud coverage of the Earth. Well, so what? How can we explain the changes of climate, local changes, for example, during this little ice age. It's not the solar system was not moving through any particular places in the galaxy. We don't know at least, but and why would it be correlated with the solar activity? It seems like a big puzzle. Why these two events can possibly be related? The issue is that solar activity is also creates solar wind, and solar wind creates this cocoon of magnetized gas around solar system, and this cocoon of magnetized gas prevents cosmic rays from the galaxy to get inside, and therefore it prevents these cosmic rays to interact with the Earth's atmosphere. So this is a very interesting explanation, which physically makes sense, and this can explain this variations of climate with magnetic solar activity. Well, whatever the climate changes, we can ask very important questions. How dangerous are any climate changes? Well, let's think about that. I would claim that global warming is not fire fatal or to the Earth's biosphere. In fact, most of the time, the planet Earth was warmer than it is now. We are still in the ice age. For most of its time, the Earth did not have polar caps. Period. For example, dinosaurs were living in Antarctica. They were hibernating during the polar night, and it's a different world. Now, Antarctica, the continent of Antarctica, is covered by 2 kilometers of ice. Therefore, we are in the ice age. So you can say, okay, if we have warmer climate, we'll have more species because compare the diversity of species at the equatorial regions and in the polar region. We have higher productivity of biosphere. We'll be happier. The problem, unfortunately, is related not to the climate change. The problem is related to the nature of humans. And what we are afraid of fighting global warming. We want to preserve the status quo in terms of climate. That's it. That's only reason why we are fighting it. Because if some places which are now very productive in terms of agriculture and living nice living conditions, and tomorrow they become flooded, the humans there will not stay. There is high density population, they will try to move, but no one in the present world will allow people to move because there are borders. And this, climate change can induce a lot of anxiety and is likely to result in the devastating World War III, which definitely will destroy our civilization. This is the slide number 49. And the last slide is my summary that the sun activity affects our civilization. I may talk about magnetic activity. It results in this ejection of energetic particles that affect our technological world, but it also induces climate variations, which affect us as a human being in a fundamental way. Thank you.
Yeah, thank you so much, Dr. Lazarian. And we'd like to inform everybody that we will be opening up the floor for questions. In case you have questions, please raise your hand. We will bring you up the stage to have an opportunity to ask questions or clarifications from our guest speaker. And I'd like to inform everyone that we are starting our YouTube channel a little more actively. And maybe later, Bob will be able to inform you as to where to search for it. There aren't many uploads in YouTube, but Bob has been syncing, just like what Dr. Laserian's lecture a while ago. Bob will be syncing his talk with the slides that he had presented to us. So in the future, it will be easier to listen to our room's replay in Quantum Photonics. It is being immortalized also in our YouTube channel. So, yeah, we have here Frank and Good on stage, and I'd like to welcome them. But in the meantime, I'd like to reset the room. We are here and we have listened to the presentation of Dr. Alex Lazarian, who is a professor at the University of Wisconsin-Madison. With a joint appointment at the Department of Physics, he started his research in the theoretical physics group led by Professor Darcel.
Cecile, we just lost you.
Hello? Yeah, I don't hear anything.
And upon getting his PhD from Cambridge, he stayed for a short period in Austin and Harvard, and later had his 3-year postdoc at Princeton University. After which he got a 5-year fellowship at the Canadian Institute of Theoretical Astrophysics, but spent only 1 year there because he got a faculty job at the University of Wisconsin-Madison, and he'd worked there since 1999. And yeah, he is a professor there, and he has been doing research. So if there is somebody who's also an author who is an authority on the topic that we're discussing now, Dr. Alex Leserian is one of the world's leading authorities on this. And I'm very glad that he was able to do this talk here in quantum photonics. It changed maybe some things that has been taught to us, at least for myself, that has been conditioned. And there is so much to talk about around just this particular topic in terms of subtopics that he has been discussing in order to maybe educate and also re-educate us. And recently, among the things that he had mentioned was that I had heard an interview with um, Bill Gates, and of course, they were speaking about in relation to what Dr. Lazarian has discussed about, the trees that we have to plant trees. But Bill Gates had made just maybe yesterday or the day before yesterday had coincidentally made this comment that why are we trying to put uh, this mitigation only on trees, because trees absorbing carbon dioxide also has a cap, but we did not think about our desert and other parts of the world as carbon sinks. So yeah, that made me very interested, and so coincidentally I researched on that because I saw the slides of Dr. Lazarian only maybe an hour ago, because as you know, we have similarities actually, because I also when I give a talk I prepare my slides on the last minute, so I understand very well how Dr. Laserian's way of thinking is. So I'd like to thank you for giving this very nice lecture. And yeah, anyway, this is my question, and after that I will pass the mic to everyone here on stage, and yeah, to other people who will be asking questions. So can you please comment on the comment of Bill Gates that I was talking about, Dr. Laserian?
Could you repeat this comment, because the transmission was not very clear. What was the particular comment of Bill Gates? Would you repeat it, please?
Yeah. Bill Gates was trying to make a comment on a comment of somebody who interviewed him, because, of course, I am also an advocate about, planting more trees. And Bill Gates was saying this is not the only way to, of course, this is a way, but this should not be the only way, that we have to think about mitigation as regards climate, because trees also have a cap on trying to be carbon sinkholes as to trying to absorb carbon dioxide. And we forgot that we have deserts and other places on Earth that are also carbon sinkholes, just like what you mentioned a while ago.
Okay.
So, yeah.
So the first of all, yeah, indeed, there was we should be careful when we are talking about trees as sinks of carbon dioxide. Consider Amazon jungles. You would say, well, wonderful. There's a huge sinks of carbon dioxide. Wrong? Well, right in the middle. Well, if you burn Amazon jungles, indeed, you will release additional amount of carbon dioxide. But Amazon jungle is an ecosystem which both absorbs carbon dioxide and emits carbon dioxide. I'm not talking about animals. I'm talking about, just consider pristine forest, jungle. What's happening with these trees? They're growing, they're absorbing carbon dioxide. But what's getting next? They die, they decay. And what's happening with this carbon dioxide, with the wood? It's getting oxidized through different biological, chemical processes, and it's released in the atmosphere. So at this moment, Amazon forests are not absorbing additional amount of carbon dioxide. So as much as they absorb, the same amount they emit. Indeed, if you make deserts, forests, reverse this deforestation happened due human activity all over all continents. Indeed, you will absorb enough, some amount of carbon dioxide. But if you allow this wood to be then burnt or just naturally decay, it happens with wild forests. In this case, this carbon dioxide will be released back. So you are not really solving any problem this way. So if one wants to solve a problem of, carbon dioxide emission by planting trees or whatever, bushes, in this case, you need to have an idea what to do with this, bushes, for example. Bushes are better than trees. They are usually growing faster. My colleague, Frank Shu, who astrophysicist who died unfortunately a year ago, came to a solution, and he suggested a process which was tested in Taiwan. So these bushes could be put in some, molten salt, and as a result, they become resistant to rotting. And he was suggesting to, put these bushes inside the earth, and found that this is good for the earth because they have this porous structures. They would accumulate water and would actually help to the biosphere. But at the same time, being in this actually coal stage, it's not real coal because it's pretty porous, but it is coal in terms of it's having a structure of coal. In this case, you will indeed have carbon dioxide, um, inside the surface. Well, it was just an experiment, and no one is doing this on the large scale, at least not at the scale anyway comparable to the scale of the coal burning or natural fuel burning. So this is therefore we do not have a good solution just relying on plants so far. At the same time, we should remember that water absorbs carbon dioxide, and it gets a different, you know, after that, chemical properties. And as a result, it starts this. It's actually forms some sort of acid, carbon acid, and this carbon acid can interact with limestone. And most of this CO2 in the history of our planet was absorbed not by plants, but was absorbed by this limestone and other, rocks. So water is an important, mediator for such a process. Therefore, this if we want to change the you know atmospheric content of carbon dioxide, we should focus on hiding this carbon dioxide in the rock, I think, because it is the easiest way, much more cost effective way compared to, for example, the ideas of pumping carbon dioxide in some cavities in the earth, or all other ideas are much more expensive and not as sustainable as hiding it in the rocks. And by the way, the disruption of I was in Cambridge and in Oxford, and the cathedrals there are made of limestone, and this limestone was under a lot of destruction due to the acid rains. What are these acid rains? Acid rains are exactly related to this chemical reactions. So we may think of other ways of getting the carbon dioxide from the atmosphere. This is one idea. The second, and probably the most important point that I made, is we are afraid not the climate change. We are afraid of our reaction to the climate change. So this is the most important message. Humans are afraid of destroying themselves with the climate change inducing their anxiety. They are afraid of their anxiety, and in the very fragile political system that we have, and with the presence of biological and nuclear weapons, this is most likely to result in the destruction of our civilization. So we will not be killed by CO2, we will be killed by ourselves as a result. Have I answered your question?
Yeah, thank you so much. You know, your questions are leading me to other questions, but maybe that is a conversation for some other time, because you presented a talk which has a lot of components this time. And yeah, I hope you can come back and try to, discuss some portions of that, because it's very interesting and it's very educational, because I'm sure that a lot of us were taught otherwise. So it is very enlightening, actually, hearing it from you, from your experience, as well as from your studies and from the scientific point of view. So thank you so much, Alex, and I will not delay anymore, because I know that there are people waiting here on stage to ask you questions, especially Frank and Good, who has been patiently waiting for some time. And hi, welcome Nas, B, and Kevin. So Frank, would you be asking questions now?
Uh, yes, thanks, Cecile. Yeah, welcome back, Alex. Another treat. Beautiful slides. Thank you. And uh, since there seems a very warm, like a lot of interest from the audience, I'll just limit it to one question. Um, on your slides 19, you briefly mentioned that there's the dynamo effects that are similar between the working underneath. There's the convective fluid, uh, you know, within the Earth and within the Sun. But I wanted to have you to give a little bit more detail because you mentioned just briefly there seems to be also glaring differences between the two systems that are at least the fluid itself are different, and also there's a very notable difference in their periodicity. There's a 11-year very regular, right? Not so much like for the Earth. Yeah, thank you for your gracing us with another great lecture.
Well, you're absolutely right. I was trying to avoid dwelling on the issues of magnetic field generation. This is a subject of a very different dedicated lecture. And you are also absolutely right that there are glaring differences between the magnetic field generated by the sun and magnetic field generated by the earth. Well, I may be talking more, professionally, if I say that indeed the dynamo process of magnetic field generation in the Earth and in the Sun are radically different, and they are called fast and slow dynamo. What is the difference between fast and slow dynamo? The slow dynamo is the dynamo which is happening in the earth. And in the earth, the conductivity of this molten rock inside the earth is low enough. Therefore, there is a process of I'm trying to find not scientific words for this, but scientifically I don't know. I will have to say use the terminology. There is a so-called magnetic helicity. It's like a spiralness of magnetic field, and the Earth dynamo destroys helicity and in its process of magnetic field generation. And therefore, Earth dynamo was possible to, simulate using computers. But solar dynamo is fast dynamo, and it's much less explored. And my collaborator, Ethan Vishniak, whom I worked with on turbulent reconnection, also formulated a theory for the fast dynamo, which can generate magnetic field in spite of preserving helicity. So again, this is a very specialized subject. Maybe you should invite Ethan Vishniak to explain you the difference of different dynamo and the essence of his theory. That's my suggestion. But for the time being, I just can tell you You are right. These are two different processes, two different types of dynamo. They have similarity that due to this hydrodynamic, magnetohydrodynamic motions, we have generation of magnetic field. But indeed, this Earth dynamo has changes of magnetic field polarity. It's also happening. But it's happening on geological periods of time. But for the sun, it's happening only over the period of 11 years. I don't know whether I answered your question, but I try to not go into specialized details.
Yeah,
Yeah.
that's great. Thank you, Alex, for the illustration. Yeah, thank you.
You're
Yeah.
welcome.
Thank you, Frank. Thank you, Alex. So, yeah, we'd like to pass the mic to Good. Good.
Yes, thank you, Cecil, and thank you, Dr. Alex, for this wonderful lecture. I'm curious to know from you, Doctor, that as you narrated, that it is much about the reaction of human being for their survival. So, what are your thoughts on our capacities to counter or to mitigate the impact of this solar field, or would we be able to control it in near future for
Well,
our benefit?
we cannot control the effect of solar magnetic activity. We cannot control the effect of this cosmic rays on our atmosphere. We cannot control it now. It's unlikely that in the foreseeable future we will be able to control this. What we potentially should hope to control, we should be able to control our actions and our reactions to some changes. Our actions, yes, if we believe that this is CO2, we should decrease this CO2 emissions. We should, but in fact, what is happening now? That the climate issues became very much politicized. And the issue here is that, in a sense, we are back to religion. Religion, when people do not want to hear opposite views, because there is a lot of money, there is a lot of power which is circulating in this within within the world due to these issues of the climate change. For example, there are conferences where people who talk about the magnetic effects, magnetic activity of the sun are not invited because the worry is, this could give additional, power to the I don't know, oil extracting companies because they will say, oh, this is solar activity. So, but this is not the point. The point is that we need to study everything properly. We need to study everything properly and objectively and understand what is going on. So the fact I also mentioned in my talk that our planet had quite a number recorded changes of climate. We know this. And we also know that these changes of climate were happening without effect of human beings. And these changes were happening over several decades. So we know that climate is something pretty, you know, pretty subtle, and we do not understand it properly. So this is one thing. I'm not suggesting that, okay, let's, have no limits on carbon dioxide emission. I'm not at this camp at all. But I'm just saying we should be scientific. This is first thing. The second thing is there can be changes in the climate. They may not be due to humans or may be due to humans. We don't know. But we should be prepared to them if we want to survive as a civilization. So, yes, we can control CO2 emission. Hopefully, we'll find a way to control it. But there can be some other changes which will happen on the period of a decade, and we will not be able to control it because it's not due to humans. If we want to survive, we must be prepared. I'm pessimistic that we will be prepared ever to that. It's not in human nature to be prepared to such things and not to start wars in the situation when one nation becomes poorer with the time or have some disasters, but at the same time, this nation has a power to move its borders. It never happened, but and we do not have institutions which can help us to solve this problem. Because if one climate changes, nations which may have now benefits from this climate will have bad effect. But nations which, for example, live in desert may have more rains, and there will be more productive land there. So if you redistribute the population over the planet, you may have you may benefit, in fact, from the climate change, or at least do not suffer too much. But all these changes usually happen with force. And we know that there were this big migrations of nomads, which at some point destroyed Indian civilization, destroyed Roman Empire. But they were moved by the climate changes. And now with nuclear and biological weapons, this will not be just a destruction of particular states of empires, but will probably be a destruction of the whole human race. I don't know whether you are satisfied with my answer.
Yeah, very much. Thank you. Thank you so much.
Okay, so next up would be B. Do you have a question or a comment for us?
Hi, good evening. Thanks, Professor, for being here. I have three short questions. Feel free to not answer all of them if there are time issues. The first is, how likely do you think within our collective lifetimes there'll be a very uncomfortable solar event, such as a 10 to 20 degree Fahrenheit increase in temperature, as mentioned in your slide, is happening several times in the last 100,000 years? Number two, what speculative technology do you think is most intriguing as a mitigating force against this? And third, do you have any favorite cultural stories about the sun, such as literary or mythological? Thanks.
Well, I think if I answer all your three questions, it would be another hour. So I will try to just briefly express my opinion. What was your first question? Because I would like
Oh, sure.
yeah.
How
Well, I
likely is
remember. I
it?
remember. I remember.
Yeah.
What is the probability of having this event? You know, we do not know. It should not be. It's like with asteroids. We believe that dinosaurs were exterminated by this impact of huge asteroids which hit our planet. It can happen, tomorrow, or in a year, that another asteroid will hit our planet and we will be destroyed completely. But the probability of this event is not so high. When I was a student, I talked with Edward Taylor, the developer of the thermonuclear bomb, and he was claiming that the most important for civilization is to build the shield against asteroids using, some means which probably with thermonuclear explosions we could divert these asteroids from the Earth. But it was 1990s. And at that time, everyone was talking about end of history. It was considered that, Pax America would be forever, and America would dictate the rules of behavior to all other countries. It will create, global market, which will help all people to reach prosperity. It will create democracy through the world. It was a different world, and therefore we should be prepared to protect this wonderful world from an impact which can happen in another million years. We are living in a different world, as you know. Our country lost, I don't know whether you're American, I am American, so I'm talking about my country. Our country lost the historical chance to build a safe world. It destroyed the United Nations, essentially. What's the role of United Nations for Gaza conflict or for Ukrainian conflict? No, nothing. It's just empty organization. The last General Secretary of the United Nations, Boutros Ghali, I think he was his name, was essentially pushed away from his office by Madame Albright because she claimed that we need in the United Nations a secretary, not a general. His title was General Secretary. So she was saying we need secretary, not a general. So yeah, we have a secretary. We don't know what his name is. At least I don't know, and I don't care. No one cares. So we do not have this authority to prevent a devastating war, and we see this now. So if you ask me what what should we really worry about an asteroid, I would say, wow, if we had less problems right now. Right now we are, as I say, we are like this frog which is being slowly cooked, and it's not jumping out of the water. If this continues, for example, in Ukraine, there will be a use of nuclear weapon. Unfortunately, I don't see any expectation different from that. And if there is a use of nuclear weapon, what will happen? God knows. Hopefully, God knows, because the world is ready for the World War III. We have this two empires, Chinese Empire and American Empire, and the situation is very similar, at least to my mind, to what was before the World War One. There was a rising German Empire, and it was a decaying British Empire, and the conflict between them was inevitable. So this is my pessimistic view. In view of that, unfortunately, we may have may be a witness of destruction of all of us during our lifetime, much more compared to any natural or even human-induced through climate change event. I hope I'm too pessimistic, and I hope that all this will not happen, and our generation and our kids and our grandkids will not die in World War III. But it's a very dangerous situation. Unfortunately, politicians all over the world do not understand what's going on, I'm afraid, or they pretend that they don't understand. No one wanted to have World War One. No one, but it happened. It was just everything was sliding to that. So it's a very, very dangerous world, and climate big change is probably not the most dangerous thing in this dangerous world. Okay, it's my perspective. You may take it or leave it. Thanks.
Yeah. Uh,
Hello?
Go
Yeah.
ahead, Bob, please.
Oh, I was going to mention that Kevin would be the next in line for my PTR. So, Kevin, do you have a comment?
Oh, yeah. But question. Yeah. Fascinating. Nice to speak with you and hear you again. I would just let's see. I was wondering if you, off the top of your head, if you remember, or if, at the moment, do you know the evidence presented by Dr. J.E. Brandenburg? A physicist from Morningstar Applied Physics. Since you're speaking of nuclear exchanges, presented intriguing evidence at the 46th Lunar and Planetary Science Conference in 2015 for evidence of large anomalous nuclear explosions on Mars. Anomalous. Um, Do you know that? Do you remember that right now, or?
No, I was not following this. I only know that there were explosions on our planet, and in the 50s and 60s there were plenty of nuclear tests. Interestingly enough, the effects of these explosions are still felt by our civilization. For example, in Germany, they found that this wild boars have a lot of radioactivity, so their meat should not be eaten. And therefore, German government gives hunters some money for them to deliver this killed wild boars to to be buried. It was initially thought that these wild boars are so radioactive because of Chernobyl, but they analyzed these isotopes, and they found that the Chernobyl isotopes are different from those that are mostly produced by nuclear explosions. Chernobyl isotopes are mostly now decayed. It's a short-lived cesium isotope, but these are long-lived isotopes produced in nuclear explosions. So, well, we can talk about explosions on Mars, but unfortunately, we had such things on our Earth. And in the case of a nuclear war, we'll have them such explosions everywhere.
Oh, okay. Yeah, yeah, and also, yeah. Speaking of isotopes, you brought that up. Yeah, the presentation also has some NASA scientists, and they said they talked about xenon isotopes. Because Mars' atmosphere contains radiogenic isotopes of xenon and argon, and they had some interesting things there that can go on. I'm sure you know about it, but so you make me think of the Tunguska event. You know, speaking of 1908, when in Russia when all the trees were knocked down. But do you think that was indeed an asteroid or?
Well, Tunguska event is a very interesting event. For many, decades, it was completely mysterious because they could not find the pieces of this asteroid. But more recent event also which took place in Russia. Don't remember. I think it's Sverdlovsk or something similar area. Showed that indeed it's very difficult to find the pieces of asteroid, and the most destruction is done by the shock wave, which are created by this asteroid as they move in the atmosphere. The very remarkable thing about Tunguska event was that for decades no forest was growing in some area. So there is taiga, and there was taiga destroyed. But we know that this northern forests pretty fast in restoring. For example, there could be a fire and they are restored in a couple of years. You have new trees, but there I'm not sure what is now, but for many decades there were no trees growing. So this is still a mystery. So there are many interesting mysteries, exciting, not answered, related to this Tunguska event. Returning back to this possible explosion on Mars, a nuclear explosion. We know that, for example, there was, if not an explosion, but a sort of nuclear reactor, natural, which worked in South Africa long time in this geological era. It happened that just this uranium got to such a concentration that there was a sort of nuclear reaction there. So potentially you can have different nuclear events not related to human activity. At the same time, you probably know that Elon Musk is thinking of using nuclear explosions, thermonuclear explosions, to create the atmosphere for Mars. And well, I don't know the details, and I don't know whether Elon Musk thought about this radioactive fallout from this experiments. But potentially we have a lot of water in the form of ice, and if, you may think of creating atmosphere in Mars. Uh, I don't know how feasible this idea, but just mention it.
Yeah, that sounds like more like publicity stunt. But yeah, I won't. There's other people I probably want to speak. I can go on. But thanks for yeah about the Mars. Yeah, that makes me think how there can be discrepancies. Yeah, thanks a lot.
You're welcome.
Yeah. Yeah, thank you so much, Kevin, and thank you, Alex. Yeah, at this point, we've been here for about 1 hour and 50 minutes. There are two speakers, Jacob and Jake, here who had been waiting on stage. But anyway, I'd like to ask you, Alex, how much more time do you have for us?
Well, if there are questions, I'm happy to answer. I was probably taking a lot of time on with my lecture, more time that I planned, and also I wanted to give more detailed explanation. So if there are people who really want to ask me, I will answer. If not, it was great to be and here and to share my expertise and my biased opinion on the subjects of both physics, politics, and climate.
Yeah, well, they are very interesting opinions and informed opinions, in fact. So, we have two speakers who had been here on stage, and Jacob just, I think, voluntarily went down. But if you want to ask questions, Jacob, please come back on stage. I think at least you and Jake deserve to ask questions because you've been waiting here on stage, and I think it's okay for Alex. So please come back on stage if you want to ask questions, Jacob. And yeah, so Jacob, earlier on the PTR, it was Jacob and then next Jake. So I'd like to give you the mic now, Jacob, and after that, let's give the mic to Jake. Thank you so much.
Sure. Bonjour, friends. Nice to see everyone. Alex, Professor Alex, thank you so much for your lecture. It's very cool. Yeah, I came on during the kind of geopolitical discussion. I was like, I'm a bit more of an optimist. I'm like, no, we will do this. Don't worry. We have the right safeguards in place, and we're slowly figuring it out as a global community, slowly but surely. But I guess in relation to physics, today I had a conversation about terminal velocity. Okay, now the reference was within the localization of Earth. Okay, and terminal speed within our atmosphere. But I actually had a question about terminal velocity for light and mass, and I was questioning why. And I'm not sure if this is necessarily very related, but this is just what is in my head right now. I'm like, how is it possible? Okay, somebody brought up that information could actually be a medium. Okay, that when we observe quantum entanglement, there's something, right? Like the rotation of the atom, it changes. And apparently it bypasses this terminal velocity. Okay, so regardless of the distance, it still happens almost instantaneously. And there was another example that it said streaming services. It said, why are people able to play video games all across the world at the exact same time? It kind of appears that it bypasses this, um, light um, terminal velocity speed. And then I was thinking, okay, it's kind of because you brought up I think you brought up something about rotation. I don't think you said sinusoidalism, but it's like even rotation, like a rotation. If we view a graph of a rotation over time, it looks like a sine or cosine model. And so I'm thinking, I'm like, okay, if if the even if the base information is just rotation, okay, we can have some sort of um, segment of information just be displayed in terms of atomic rotations. And if that's the case, then we could basically have uh, um, infinite immediate information transfer by entangling atoms and possibly more stuff. And then I'm like, okay, well, how do I entangle stuff? Anyway, this is on my mind. What do you think of this? And finally, the potential for some sort of a, I don't know, rotationary medium. I'm like, if if all mass runs on space time, but it's possible for information to bypass the physical limitations, I'm like, maybe there's like a meta layer under space time that's made out of like rotations, for example, something like that. These are my thoughts.
Okay, so you asked quite a number of difficult questions. Let me first reply to your first opening geopolitical statement that you are optimist. I wish I were also an optimist, and I wish
We need to hang out
I
more. I'll
were.
inspire you.
I wish I could believe in the better outside. Believe me, I don't want myself to die. I don't want my son to die, and I don't have any grandchildren yet, but I hope to have them, and I don't want them to die. So you are saying that we're gradually figuring out how to avoid the catastrophe. In the last 20, well, maybe probably now nearly 30 years, what we've done is, and this, my country is responsible, the United States. We dismantled the um, uh, constraints that existed that prevented the world from going into the nuclear and biological war abuse. And in this case, uh, it's. I hope there will be new constraints that will be developed very fast. Otherwise, without the development of these constraints, we are doomed. You also mentioned this terminal velocity, and this is your main question. You know what you refer to. You refer to Einstein-Rosen paradox, and it's maybe getting us a bit beyond the elementary discussion, but there are these uncertainties in quantum mechanics. And these uncertainties in quantum mechanics were interpreted by a great mind, physicist Heisenberg, in terms of so-called Heisenberg microscope. Heisenberg was saying, okay, imagine that I want to look at electron. And how can I watch electron? I should send photons, and I should send very hard photons to find the exact position of the electron. So, but these hard photons would collide with my electron, and they will change its momentum. And this is how Heisenberg explained the relation between in quantum mechanics. You want to see something very small, and therefore you also need to use some energetic particles. For example, photons, and these photons disturb your position, and this is the origin of quantum uncertainty. Later, and then this was a question whether there are some hidden parameters. So in this interpretation, you see there is electron does have at every moment its momentum and position. But when we want to measure it, we disturb its position. Very natural explanation. Then Einstein and Rosen posed a thought experiment, which you actually described. You have, for example, two nuclei which have initially no spin rotation, and then when this nuclei is divided into two, the total spin, total momentum should be zero. So what we can do, we can keep one nuclei here with us, another we can move to Mars and measure something on Mars. And if we measure something on Mars, we will also know that, for example, there is a spin of 1. So to have a total spin 0, it means that our spin should be 0. So it would mean this indeed a paradox, because it would imply the transformation of information with the speed higher than the speed of light. So but this is if indeed the particle or quantum object has physical properties hidden with it. So it's if this quantum particle behaves as a classical particles that we know. Okay, but then came a scientist Bell, and he introduced so-called Bell inequalities. And this Bell inequalities were experimentally, proven to be correct. And these Bell inequalities, I will not go into details, shows that the quantum objects do not have the properties before their measurement. How to explain this paradox, Rosen-Einstein paradox, is mind-boggling. We cannot explain it. There's no reasonable explanation for that. And Bell, who formulated this Bell inequalities, which were proven to be correct, was claiming that I do not understand quantum mechanics. Other people were saying, why? We have equations. We can calculate the probabilities. Everything is fine. But he was saying, I want to understand this physically. It does not make sense. I was in Cambridge, and there is a club of people seriously confused with quantum mechanics. Nobel Prize winners are members of this club. So it's something that we do not understand. We do not understand quantum mechanics. We understand relativity, we understand general relativity, special and general, but we do not understand quantum mechanics. We can use these laws. We're now creating quantum computing on these laws, but we do not understand how it works. So it's not the issue of the terminal velocity or no terminal velocity. No, no signal propagate faster than light. These particles in this Einstein-Rosen experiment do not communicate with each other, but they have this unexplained quantum properties. I know that it's not a satisfactory explanation. I wish I could understand quantum mechanics and explain to you, but no one in the world understands quantum mechanics. If someone tells you in future that this person understands quantum mechanics, either it's a super genius person or just an ignorant person. So, well, that's my answer to you.
Thank you, Professor Alex. You know what's interesting? I actually feel satisfied because it wasn't even necessarily about terminal velocity. It was a room about terminal velocity that I first asked this question, and it was earlier today. But your answer was a lot more satisfactory. And even knowing that there's Nobel Prize winners and a group at Cambridge for people who are just like, look, I just want to understand. Yes, we have equations, sure, but just help me actually feel like I understand the process. Well, we'll get there. We'll get there slowly but surely. Yeah.
Well, you are very optimistic. I'm happy to talk with optimistic people. I'm more, I don't know, between realist and pessimist. Hopefully, I'm just pessimist and realist are right.
Yeah, thank you so much, Alex. So I think it's getting late, but I must tell you that we are very privileged, everyone, to have Professor Lazarian here. who is knowledgeable in many fields, especially, of course, on the topic that we have. But he has been to many esteemed institutions like Cambridge, Oxford, Harvard, and Princeton. And yeah, it was, and we are very privileged to learn also from his experience and discussions and explorations with other experts. So it's like we are sitting on the shoulder of a giant. So I want at this point to tell you, Alex, that we hope you can come back here even for a general discussion, because the lecture that you gave today gives rise to a lot of other side topics which are really informative, at the same time also controversial, and at the same time very educational to all of us. Thank you so much. And I think Jake will have the chance, the opportunity to ask the last questions. I'd like to give comments on some comments here on the room chat. I think there was someone who said that was talking about the dinosaurs and dark matter, uh, about the book of Lisa Randall, which has been published several years ago. Maybe this is an opportunity for us also, or a chance for us to invite Lisa to come here. I'm not sure if she has been invited in Clubhouse, but yeah, for the interest of time, our speaker might not have the chance to answer, and we will note all the comments that you had made here, including like the trips to Mars and also the atmospheres there, and yeah, there were a lot of other subtopics. So, but at this point, I'd like to give the microphone to Jake, who has been waiting patiently to ask the last question. Jake?
Hi, thank you, Cecile, and thank you for your time, Professor. And my question is going back to climate change. And are you saying that this intergalactic magnetic fields have a bigger influence on climate change than uh, the human carbon emissions?
No, I never said that. I never said that. I don't know. Well, let me be very careful, because it's a dangerous subject to make any comments. First of all, let me explain what I was showing you. That there are significant changes. Some are global changes on the periods of millions of years. And these changes definitely are not related to human activity. Climate was changing. There are some theories which related to the change of the axis of precession of axis of rotation of the Earth. There are such theories. What I showed you is that there is a very good correlation between the changes of the uh, climate, Earth climate, and the passage of the solar system through the galactic spiral arms. So, this is the issue of billions of years, and there is no issue here at this time about human activity. Then, there is another piece of data which I showed. I'm showing just data to you. There are, peer issues related to for example, little ice age, which coincided with the period of lower sun activity. This also, it was a cold period, but it is related to solar activity, magnetic activity, solar magnetic activity. So not related also to humans. There are also additional things which could be related to the eruptions of big volcanoes. It also introduces natural changes of the climate on the shorter periods of time. So there are many reasons that the climate can change due to factors which humans have no control. So this is only my statement. And these all factors should be considered when we are considering what is happening now. I'm not an expert in this field to say to what extent any of these factors are important. Okay, so these are natural factors. There is also definitely human activity, and we know that we are changing the amount of greenhouses, gases, greenhouse gases in the atmosphere. It's another factor to be taken into account in this equation. So the becoming electric, getting more generation by solar power, it's wonderful. It's definitely better to use oil, not to burn it in our car engines, but it's better to use it for producing some new materials, for example. It's much better use of this natural resources, and it's better to use renewable resources. If
Okay,
our
great.
civilization survives longer, we will definitely need thermonuclear energy to satisfy our needs and to expand from the Earth to further solar system, to have new habitable worlds elsewhere. We will need this solar energy coming to the sun, to the earth, will not be eventually enough for us. Because through all the history of mankind, the growth of energy demands was exponential. And we are coming to that. We are coming to that, understanding better magnetic fields, understanding confinement of plasmas by magnetic fields. There are the tokamaks in China. There is in Europe tokamak, international tokamak, and it will be eventually achieved, provided that the civilization survives. So, well, that's my again final note. We should now, I think, worry more about the survival of civilization compared to anything else.
Okay, and just a question about these. Um, I'm assuming these intergalactic magnetic field particles are higher energy than the particles coming from the sun,
Yeah,
and
you are right. Yeah.
we have solar storms. Is it possible to have a storm of these intergalactic magnetic field particles? And do you think we've had them in the past?
Well, these particles are more diffuse. They are, they are not in the sun. We have these blobs of particles which are thrown in the direction of our planet. So therefore, we have the storms. But in what is happening in the galaxy, these particles are more diffuse. But you're right that potentially we can have a particular event. For example, there can be gamma ray burst or hypernova very powerful supernova, or supernova with a concentrated beamed flow of particles, energy, and indeed such event could result in a huge flow of particles, storm of particles, and it could be terrible. If, for example, this gamma ray burst happens in the vicinity, in the some maybe dozens of parsecs from us, we would be cooked here. We could on the Earth because of the high energy particles which can come. So, yes, but again, it's more likely that humans will cook themselves rather than waiting for any external impact to kill them.
Well, it seems like okay, you're mapping these magnetic fields, so that must mean that there's areas of sort of higher concentrations of
Well, magnetic fields, well, there are two things. Magnetic fields like rails, and particles may move along these rails. So the magnetic fields do not, unless they reconnect as they're happening on the sun, they are not giving energy themselves. But
right,
they are like rails. But
but
this particle, yeah, sorry.
but can't they sort of like a particle accelerator is magnetic fields and they focus a beam. So that was what I was sort of
Okay,
referring to.
sure, sure,
If
sure,
we
sure.
drift, yeah, if we
Yeah,
drift into like a concentrated area of this magnetic field where the particles are sort of focused, that would be an issue.
right. Well, you see, we know magnetic fields structure around our in the solar neighborhood. I would say relatively well to avoid encountering to somehow dismiss the probability or possibility that there is some magnetic tunnel in the vicinity of the solar system. So it's not a worry. But you're right that these particles in the energetic events can be beamed. They can go not in all directions, but due to magnetic field at the source, they can be directed in a particular direction. We know a lot of astrophysical jets which show a high degree of beaming. Our understanding of gamma ray bursts also includes this beaming. So, indeed, we can have accelerators which will send beamed radiation in direction of the Earth. The however, the most likely we will encounter the beamed gamma rays because, as I said, magnetic fields in the galaxy are more, random. And therefore, even if you send a very beamed, a beam of particles, focused beam of particles. They will be affected by this random magnetic field and will be scattered around. But gamma ray bursts that are produced in the jet, they can be beamed, and if we are unlucky that there is a gamma ray burst in the vicinity of our solar system, and this beam is directed towards us, we may have big problems in terms of significant damage to biosphere.
Great. Thank you very much.
Well, you're
Yeah.
welcome.
Thank you, Jake, and thank you, Alex. We would like to listen more to you, so I hope we can invite you again to even have general questions related to this topic. And anyway, we are very appreciative of your coming here and for trying to refer to us very competent and excellent speakers. So I'd like to ask at this point. Bob, to if you have something to say or if you have a question, I'd like to give the mic to you. And after that, we will thank our great speaker, Dr. Lazarian. And of course, we will pass the mic to Darcel to help us close the room. And in the meantime, Bob, can you say something about your YouTube channel for Quantum Photonics, where they will be able to hear the replay of this conversation with Dr. Lazarian very soon? Thank you.
Well, yes, what we've been doing is taking audio from Clubhouse and mixing it up with the slide decks and then putting out little YouTube movies. And it usually takes me a few days to do it, so it'll be a couple of days before this conversation is up. But if you look for us on YouTube, and it's just Quantum Photonics Club, is how to find us. And I wanted to say on behalf of everybody in the audience, thank you. This has been a tremendous Friday night for us. So um, I thank you very much.
Yeah, before we pass the mic to Darcel, I'd like to hear from our special guest speaker, Alex. If you have some last message for us before we close the room.
Okay, thank you for your interest, and I appreciate you inviting me and also speakers whom I suggested. I can suggest also Ethan Vishniak, my collaborator, with whom we suggested the model of turbulent connection, and who himself developed the model of dynamo. He is definitely the best expert in uh, dynamo and generation of magnetic field in astrophysical media. Whether he will be uh, uh, free to have give such lecture, I don't know, because he is a general editor of the biggest astrophysical magazine, astrophysical journal. But you may ask him, and I believe that if he agrees, you will learn more about this generation of magnetic field in astrophysical media.
Thank you so much. I will email you to ask you the details, and of course, I will always notify Frank because this interest arose from his question earlier. Thank you, Frank. So, uh, I'd like to give the mic. I know there are a lot of questions here at the room chat, and wait for our great speaker to come back here again, and because I think the questions require a very long conversation. So, thank you so much again, Alex, and everyone. And we really appreciate it. And we had so much fun in this room. So at this point, I'd like to give the mic to Darcel to help us close the room. Great, great room. Darcel.
Thank you, Cecile, and thank you, Doctor, for a great room. To close the room, we're going to start our countdown from lucky number 9. Is everybody ready?
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 9,
Nine.
Nine,
Nine,
9,
Jacob 8.
8,
Ocho.
Jake 7.
7,
Kevin 6.
Sixer.
Good 5.
5.
Frank 4.
Quattro.
Bob 3.
3 it is.
Cecile dos Eques.
Dos Equis.
Good doctor, you're numero uno. Call out our last number, please.
1.
Thank you so
Woo!
much, Lazarian. Let's flash our mic for our speaker.
Sorry,
Good
Cecile.
Good night, everyone, and
Good
see
night.
you in the next rooms. Our next room will be epistemological computer scientist Monica Anderson, who's also coming as a recurrent speaker, and she will be speaking about the alignment of large language models, and as well as she will be speaking about jailbreaking. So please try to look out for that coming room. So thank you and good night, everyone.